Imagine taking a healthy, developing human embryo, sealing it inside this specialized microscopic plastic straw, and just plunging it directly into a vault of liquid nitrogen.
Right, into negative 196 degrees Celsius.
Yeah, exactly. And for the next 10 or, maybe even 20 years, the biology inside that straw is perfectly suspended in time.
Completely paused.
But think about this. What happens if, say, the ink on the label just flakes off in the cold?
That would be, well, a disaster.
Right. Today, we are looking at a security system designed for an environment where an error rate of 0.1% isn't just some statistical rounding error, it's an absolute catastrophe.
Oh, absolutely.
Welcome to the deep dive. Whether you are prepping for a medical career or you're just insanely curious about how absolute trust is engineered from the ground up, our mission today is to map out the invisible, high-security defensive network protecting patient sample identity in the IVF laboratory.
And it is a completely different way of thinking about safety, really.
How so?
Well, in most industries, a very low error rate is, an acceptable metric for success. But in the embryology lab, the accepted error rate for sample identity is absolute zero.
No, zero.
Exactly zero. It's not just some lofty goal on a motivational poster. I mean, it is the baseline requirement before the lab even opens its doors.
Because the stakes are just too high.
Right. We are dealing with the foundational building blocks of human life. So the architecture we use to track every single tool, every petri dish and test tube, it has to be a living, active system.
Okay, let's unpack this. Because achieving an absolute zero error rate in any human endeavor sounds, well, conceptually impossible to me.
It does sound like a lot, yeah.
My mind immediately goes to something like a financial blockchain, where every single movement of an asset requires an independent stamp, a signature, and some mathematical confirmation before it can move to the next ledger.
That's actually a really good comparison.
But biology is infinitely messier than digital currency. So where do you even start building that chain of custody?
Well, we start by mapping out what industrial safety engineers call critical control points, or CCPs.
Okay, CCPs.
Yeah, think of these as highly sensitive vulnerability windows. A CCP is any specific moment a biological sample changes containers, moves between workstations, or transitions from one staff member to another.
So basically, anytime something moves or changes hands.
Exactly. And at these exact checkpoints, verification isn't just a best practice, it is legally and clinically mandatory.
Let's walk through that practically just to give the listener a visual. If a patient is going through a cycle, what does that first critical control point actually look like in the lab?
The first major checkpoint is the oocyte pickup.
That's the surgical retrieval, right?
Right. The follicular fluid is drawn from the patient in the procedure room and passed through a physical window directly into the lab in test tubes.
Okay, through a literal window.
Yes. And those specific test tubes must be perfectly matched to the primary culture dish that's waiting on the heated lab bench. The lab is verifying the identity of every single oocyte recovered right at the origin point.
Got it. And then parallel to that process, you have the sperm processing happening elsewhere in the lab, right?
Exactly. Someone is verifying a raw semen cup against a series of wash tubes to prepare the sample for fertilization.
Which involves a lot of moving parts.
It does. Which brings us to the most delicate, high-stakes intersection of the whole process, the ICSI procedure.
Let's pause and define that for the listener, because ICSI, intracytoplasmic sperm injection, is quite an intense procedure.
It is incredibly intense, yes.
Instead of just mixing eggs and sperm in a dish and, hoping for the best, the embryologist is physically selecting a single sperm cell and injecting it directly into a single egg using microscopic glass needles, right?
That is the exact mechanism, yeah. It requires intense, completely unbroken focus.
I can imagine.
I mean, the embryologist is looking through a high-powered microscope, manipulating those glass needles with joysticks and tracking the exact maturity of the cell all at once.
That sounds like performing surgery with a video game controller.
Pretty much. They have to verify if they are looking at an M1 or an M2 stage oocyte.
Meaning the developmental stages of the egg, right? An M1 is an immature egg.
Right.
Whereas an M2 is mature and fully ready to be fertilized.
Correct. Every single microscopic attribute, whether it's an M1 or an M2, is documented and inextricably tied to that specific patient's identity.
Okay, wow.
And from there, the material either goes into a highly controlled incubator, leaves the lab to be transferred back to the patient, or it goes into the sub-zero vault for long-term cryopreservation.
Okay, I have to play devil's advocate here for a minute.
Sure, go for it.
We are talking about highly trained clinical scientists operating in a highly regulated medical environment. Why does just reading a label and checking a name require a military-grade security architecture? I mean, humans read labels perfectly well every single day.
Well, we like to think we do.
We don't.
Not really, no. What's fascinating here is that the human brain is actually fundamentally flawed when it comes to highly repetitive, high-stakes tasks.
Interesting.
Historically, the baseline for lab security has been manual double witnessing.
Okay.
Embryologist A reads the label out loud. Embryologist B checks the destination dish and verbally confirms. It's vital, but it relies entirely on human attention.
And human attention inevitably fatigues.
It doesn't just fatigue, it actively tricks us through a psychological phenomenon called involuntary automaticity.
Involuntary automaticity. What does that mean exactly?
Well, when an embryologist looks at hundreds of identical white medical labels a day, the brain tries to conserve metabolic energy. It starts taking cognitive shortcuts.
Oh, so it's like driving home from work. You pull into your driveway, and you suddenly realize you have absolutely no memory of the last 5 miles.
Exactly.
You stopped at the red lights, you made the turns, but your brain was running entirely on autopilot.
That is the exact mechanism just applied to a medical laboratory. In the lab, due to sheer repetition, your brain starts seeing what it expects to see on the label rather than the actual printed letters.
Wait, really?
Yeah. You could stare directly at a mismatched name, and your brain's automation bias will literally autocorrect the visual input to the name you were anticipating.
That is terrifying in a medical context.
It really is.
It's exactly like proofreading an important email and reading right past a glaring typo, because your brain already knows what the sentence is supposed to say. You aren't seeing the pixels on the screen, you're seeing your own thought.
Yes. Recognizing that biological limitation is the absolute first step in designing true safety. We can't just mandate that staff, try harder to pay attention.
Right, because the brain is going to do what the brain is going to do.
Exactly. We have to design systems that forcibly jolt the brain out of autopilot. That's why the manual double witnessing requires verbalizing the information out loud.
Because speaking breaks the autopilot.
Right. But to hit that absolute zero error rate, the lab needs a partner that doesn't have a subconscious mind trying to cut corners.
Here's where it gets really interesting, in my opinion. Enter the electronic witnessing systems.
Yes, the electronic shield. These systems cast a continuous, invisible grid of protection over the entire workspace.
Like a safety net?
Exactly. It's a tireless third partner operating in real time alongside the embryologists.
So let's visualize how this works on the physical bench. We are dealing with microscopic cells inside tiny plastic dishes.
Yeah.
How do you electronically tag something that small without disrupting the workflow?
We use 2 main architectures. First is optical barcoding. The lab prints a unique, high-density data matrix on every single dish and tube.
Like a QR code.
Sort of, but it holds far more data than a standard grocery store barcode. Above the workspace, there are specialized optical cameras. The moment a dish slides under the lens, it's scanned automatically. This instantly pulls up the patient's entire electronic file on a monitor directly in front of the operator.
That covers visual confirmation nicely, but there's a wireless layer that feels almost like science fiction.
Oh, you're talking about the radio frequency identification, or RFID system?
Yes, exactly.
We attach microscopic wireless tags to the very bottom of every petri dish. The laboratory benches themselves, specifically the heated microscope stages where the embryologists manipulate the cells, are embedded with hidden RFID antenna pads.
So, picture the setup for a second. The lab is dimly lit to protect the embryos. The embryologist is hunched over optics, manipulating glass needles on a heated metal plate. And hovering invisibly right above that plate is a localized radio frequency bubble, constantly interrogating those tags.
Right.
I imagine anyone listening might be a bit anxious about blasting developing embryos with radio waves.
Yeah.
Is that entirely safe?
The engineering here is incredibly delicate to ensure it is completely safe. The antennas emit ultra-low power electromagnetic fields, so they're very weak.
Very weak. They are explicitly designed to read the microchips under the plastic without transmitting any harmful radiation or heat to the biological material inside. It is a hyper-localized, fine-tuned field.
Okay, so let's play out the worst-case scenario. Say the manual checks fail, involuntary automaticity kicks in, and an embryologist places a tube belonging to patient A and a dish belonging to patient B inside that same invisible radio bubble on the heated stage.
Right, a mix-up.
What actually happened?
The system instantly and violently objects.
Violently.
Well, the moment those mismatched RFID tags enter the same electromagnetic field, a piercing audio alarm goes off in the lab.
Oh, wow.
Yeah, and more importantly, the workstation screen locks down. The digital workflow physically freezes.
So it's a hard stop.
An absolute hard stop. The embryologist cannot access the patient record, cannot print the next label, cannot proceed to the next step.
It just shuts them out.
Exactly. The system forcibly stops the physical manipulation before the embryologist even has a chance to pick up a pipette. That failsafe is brilliant. But, let's take a step back. Having a blaring alarm is great for stopping an error in progress, but how do we prevent physical clutter from causing an incident before the alarm even needs to go off?
That is a great question.
You don't want those dishes getting near each other in the first place, right?
Right. This is where physical space design intersects with behavioral engineering, because technology is really only as good as the environment it operates in.
Makes sense.
To eliminate the physical risk of cross-contamination, laboratories enforce a strict spatial boundary known as the single-patient rule.
Meaning one patient and only one patient at a time.
It is a non-negotiable law of the lab. Only one patient's biological material can occupy a workstation or micromanipulator at any given moment.
So no multitasking with different patients.
Never. You cannot have patient A's oocyte dishes on the left side of the hood while preparing patient B's sperm wash tubes on the right.
Right. That would be a disaster waiting to happen.
Exactly. Between patients, the entire heated stage is completely cleared, sanitized, and the system baseline is re-verified to prove it is empty.
So it creates a literal physical moat around the samples.
A moat is a good way to describe it, yeah.
But the environment in the room itself has to be controlled too. I mean, if you were listening to this right now while driving or working in a busy open-plan office, think about how often you get interrupted by a phone ping or a coworker asking a quick question.
Oh, constantly.
Right. But in this lab, during a critical point, an interruption isn't just an annoyance. It is a catastrophic system risk.
Which is why the embryology lab borrows heavy operational protocols from commercial aviation.
Aviation.
Yeah. Specifically the sterile cockpit rule.
Right, like when a commercial flight is below 10,000 feet taking off for landing, the pilots are strictly forbidden from chatting about anything other than flying the plane.
We apply that directly to our critical control points. During a high-stakes moment like loading an embryo into a transfer catheter or plunging a cryo straw into freezing liquid, all non-essential conversation in the lab must completely stop.
Total silence.
Total silence. No phone calls, no walking past the station, no background chatter. The environment drops into utter silence.
That is fascinating. It forces the staff to treat these steps as high-focus, active procedures, not just mundane administrative chores. The silence itself becomes a tool for situational awareness.
Silence is the sound of safety in those moments. It trains the brain to recognize fatigue checkpoints and to deeply respect the gravity of the physical movement they are executing.
So we've built this unbreakable system at room temperature. We've conquered human distraction, spatial clutter, and autopilot brains. But biology requires suspended animation. How does this digital fortress hold up when you take a sample off a cozy 37 degrees Celsius heated stage and drop it into a liquid nitrogen tank at negative 196 degrees Celsius? Traditional adhesives and markers just shatter at that extreme, don't they?
They completely fail. Over 20 years of sub-zero storage, standard glue turns to dust, paper becomes brittle and snaps, and ink bleeds into illegibility.
So standard labels are completely useless.
Totally useless. You cannot rely on anything that is merely attached to the vessel.
So how do you maintain an unbroken chain of custody if the label disintegrates?
You don't use a label, you use the physics of laser-etched security.
Laser etching.
Yeah. Modern labs employ direct laser etching machines that actually cut the patient's identifying data, including those high-contrast matrix barcodes, directly into the chemical-resistant plastic of the cryo straws and vials.
So the label isn't printed on the plastic. The label IS the plastic.
It is physically carved into the vessel, and the design features massive redundancy.
How so?
The text and the matrix codes are etched deep enough that they are guaranteed to be readable by both human eyes and automated optical scanners decades into the future, regardless of how much frost builds up.
Okay, that brilliantly solves the deep freeze problem inside the vault. But what happens when a sample actually has to physically leave the fortress? Let's say a biopsy tube. A tiny sample of cells taken from an embryo needs to be shipped out to an external genetics lab for DNA sequencing.
Right. That introduces what we call the two-laboratory bridge.
The two-laboratory bridge.
Yes. When a physical sample leaves the IVF lab, the chain of custody has to stretch across state lines without breaking. We start by securing the physical transit coolers with tamper-evident seals.
Okay.
But the real mechanism securing that transport is digital.
I imagine you can't just hand a cooler to a medical courier and just hope for the best. There has to be a digital tether connecting the physical box to the lab's mainframe.
Exactly. When the IVF lab prepares the shipment, their internal database generates a secure, encrypted electronic manifest and uploads it directly to the receiving genetics facility's cloud server.
So it creates an unbroken digital bridge.
Yes.
So paint a picture of the receiving dock at the genetics lab. The courier walks in with the cooler. What happens mechanically?
The intake technician at the genetics lab scans the barcode on the incoming tube. Their local system instantly queries the cloud to cross-reference that barcode against the electronic manifest sent by the IVF lab.
So they check the ledgers against each other.
Right. And if there is a single character out of place, or if a tube is missing, the entire intake process physically halts.
Just like the heated stage alarm.
Exactly like that. The system will not allow the genetics lab to log that sample into their workflow until the discrepancy is resolved.
It's that blockchain analogy returning. Both ledgers, the sending lab and the receiving lab, have to perfectly agree before the transaction is validated.
Precisely.
But let's be incredibly grounded for a second. All of this technology, the optical scanners, the laser etchers, the localized radio frequency bubbles, the encrypted manifests, it all still requires a human being to manage it.
It does, yes.
And humans, no matter how dedicated, will eventually make a mistake. Someone will grab the wrong tube or scan something out of sequence.
Absolutely. And that reality is the final, most crucial layer of the defensive network. Okay.
If we connect this to the bigger picture, how a laboratory handles those inevitable microdeviations, what we call near misses, determines the true structural integrity of its fortress. The ultimate defense isn't actually a barcode. It's a psychological safety framework known as a just culture.
A just culture. Let's break down how that actually operates in practice.
Historically, in medicine, if someone made an error, the immediate instinct of administration was punitive. Punish the operator.
Right. Find who messed up and fire them.
Exactly. But a just culture completely shifts the paradigm away from individual blame. Let's say an embryologist, at the end of a very long, exhausting shift, accidentally brings a mismatched dish to the bench.
Okay.
The RFID system catches it, the alarm blares, and the screen locks.
So the system worked. Nothing bad happened to the sample, but an error almost occurred, a near miss.
Right. In a traditional punitive culture, the embryologist would be terrified of being fired. They might try to hide that the near miss ever happened.
Oh, absolutely. But in a just culture, that exact event is openly reported, documented, and actually celebrated by the management as a successful stress test of the electronic shield.
Celebrated.
Yeah. It is viewed as a victory for the system, not a moral failing of the human.
That is a massive operational shift, because if you punish a near miss, you just drive the errors underground. Staff will inevitably figure out workarounds to bypass the alarms just to avoid getting flagged and reprimanded.
Exactly. Fear breaks security. By encouraging staff to report these near misses without the threat of termination, the lab gathers an absolute goldmine of telemetry data.
Data they can actually use to improve.
Right, they can analyze the underlying root causes. Why did the near miss happen at 4 p.m. on a Thursday? Was the overhead lighting casting a shadow on the barcode reader? Were the labels printed slightly off-center? Was the embryologist's chair unergonomic, causing physical fatigue?
So the lab uses that near-miss data to actively harden the software and the physical architecture.
It becomes an evolutionary cycle. They redesign the software interfaces, they adjust the physical layout of the workstations, they rewrite the protocols. The entire goal of a just culture is to engineer the environment so that the correct action becomes the path of least resistance.
Take the right thing easy.
You make doing the right thing effortless and doing the wrong thing physically and digitally impossible.
So what does this all mean? Taking a step back and looking at the full spectrum, we've traced this incredible high-stakes journey today. For the very first oocyte pickup, through the invisible radio frequency bubbles and the absolute reverent silence of the sterile cockpits, down into the laser-etched sub-zero vaults, and finally into a blame-free reporting culture that uses data to constantly rebuild itself.
It's a lot.
It really is an impenetrable fortress.
True laboratory excellence is fundamentally invisible. When a patient walks into a clinic, they don't see the laser etching or the RFID loops embedded in the metal.
Right, they just see the waiting room.
But the physical confidence of the embryologist handing over a sample, knowing with absolute certainty whose future is in that dish, is entirely backed by this massive digital, physical, and psychological infrastructure. Security at this level is the ultimate expression of medical care.
That is such a profound perspective.
Yeah.
It really is an act of deep care, and it makes you think about the complex systems running quietly in your own life. Think about how many near misses happen every single day in our hospitals, our aviation networks, or our data grids, quietly caught by invisible safety nets. Nets built by engineers who fully expect us to be delightfully, vulnerably human. It's something to appreciate the next time a system alarm beeps and stops you from making a simple mistake.
Definitely.
Well, thank you for joining us on this deep dive into the vault. Next time, we'll dive into episode 19, Quality Control and Quality Assurance in the Embryology Lab, where we explore the hidden engineering metrics and key performance indicators that make this precision possible. Until then, keep looking deeper.